Welcome to this episode of the NewSpace India podcast, a show to keep you informed and engaged on India's space activities. The study of stars, galaxies, and the universe has always been of interest to humankind. In this episode of the NewSpace India podcast, Dr. Abhijeet, a researcher at the Astronomy Institute of Czech Academy of Sciences in Prague, joins me to discuss what astrophysics is all about and how to build a career in astrophysics in India. Welcome to this episode, Abhijeet. Thanks for taking time for doing this.
Thank you so much for having me.
Tell us a bit about what is exactly astrophysics and, what do astrophysicists do?
So astrophysics is essentially a study of the heavens, and people have been doing that for thousands of years. We have studied stars and planets going around the Earth, and then we turned that to a heliocentric model of planets going around the sun, and then the greater universe that people are studying. So in astrophysics, there are three different areas that people study. One is the observational astronomy, where people are looking at stars and galaxies and planets and trying to understand how the universe works. And there are people who are building the telescopes for doing that. So there are people doing instrumentation, where they build satellites such as Hubble telescope or ISRO's AstroSat or the upcoming NASA mission James Webb Space Telescope, as well as ground-based telescope. For example, India has several optical and radio instruments like GMRT and also similar instruments, but also you have instrumentation building and satellite building for planetary missions. So for example, India's Chandrayaan and Mangalyaan missions and similar missions of international communities. So that is the instrumentation side. And the third part is the theoretical side, where people are studying theoretically with pen and paper or with computers how the universe works and how the universe is structured largely. So people there will study how the gravity works in the universe, as well as what are the models of universe and how the universe behaves and expands, or how galaxies are formed, or how galaxies evolve and stuff like that.
Okay, so when you take this three different branches of what you talked about, how is it being organized in India at the moment, and who are the people behind each of these streams?
So in India and essentially everywhere in the world, many of these institutes are working intertwined with each other, but there are, of course, some differences. Most of the theoretical and observational astronomy work is done at educational institutes and research institutes, such as IUCAA and NCRA in Pune, or IISc and IIA in Bangalore, while they also often perform instrumentation tasks. So people in the groups there will be building instruments for the telescopes or for the satellites and so on. But most of the sort of space science work, where building and launching satellites and providing infrastructure for that, is provided by ISRO and similar institutions in India.
Okay, so from what I get it, to put it very simply, there's one bunch of people who are doing theoretical stuff, which is looking at the universe and theorizing many things and many phenomena and trying to understand what is going on out there. And they're using the legacy of scientists before them who have done certain work, and then they're building on top of that. And they don't need any kind of instruments, any kind of data which is observational, or space satellites themselves, but they are kind of building on the physics of the things before.
Partly, yes, but you also always want to check your theories against the observations.
Yeah.
So you're always checking your results of your theoretical work or your simulations in computers, and you're comparing them with what is observed in the world. So that's what differentiates physics from mathematics, in the sense that you want to see whether your theories are correct and are applied to our universe or not.
Okay, so that's one bunch of people.
Yes.
The second bunch of people are actually either building telescopes on the ground or building telescopes that will fly on the satellites, and then they are actually doing the instrumentation bit. So they are acting partly as kind of engineers and scientists at the same time.
Yes, that's usually what happens, is that you have input from the scientists who want to observe something or who want to study some phenomena in the sky, and they interact with engineers, as well as they themselves act as engineers to build telescope that will eventually observe these phenomena.
Okay, so then these people have the kind of skills where you understand a bit of engineering and at the same time a bit of astrophysics.
Exactly.
At the same time.
Yeah.
And then the third set of people you talked about were people who do only observation-based science, where people essentially are using these telescopes to then operate these telescopes, which are either on the ground or in the sky, in space, and then they collect data from there, and then they are trying to do some kind of data analytics and data-based sciences to basically come out with observing certain phenomena that is happening.
Yes, so that's what most of the observational astronomers will do, is they will either apply for new observations to the telescopes, either space-based telescope or ground-based, and then they will get the data from the telescope and use that for doing their scientific analysis. Or they might use some archival data available already at the telescopes. And in astronomy, most of the data provided by the telescope is proprietary only for 1 or 2 year period, and after that it becomes public. So even if you don't have association with a telescope or organization, you can still use those data and use them for your analysis.
Okay, so let's say I am a person who is now interested in astrophysics as a kid growing up in India, for example, right? Is there enough knowledge on the ground for people to choose these, when they're in high school or in college or somewhere, where they understand that there are these three different streams that are available, and how is this organized?
I'm not sure if the knowledge is available towards high school students, because at the high school level, we are not exposed too much to astronomy in general anyway. Our high school textbooks rarely mention astronomy or space science, and there is a dearth of information about what are options for you in this field. So that is quite lacking, but also people are not aware of different career opportunities in space sector as well as in astronomy, and that is also not provided to students too much.
You personally, for example, right, you have gone through this journey of doing everything, and you've completed a PhD, and you're a practicing scientist in the field. So in your personal journey, how was it, when did you actually know that, these are the streams in astrophysics, these are the things that you wanted to do or not wanted to do, and how did you acquire this knowledge?
So my interest in astronomy and scientific research grew out of reading a lot of science fiction when I was in my high school, and at that point, I decided that I wanted to do astronomy, and then I read a lot of books. I talked to a few people, and being in Pune was advantageous because we have a couple of really good astronomy institutes where I could go and talk to the researchers there, and they advised me what are the possible paths available. And once you get into undergraduate studies, then you can decide what exactly you want to do and what streams you can take and what different paths that are available for you. And for me, I decided to go towards a bachelor's in pure science. So I had my BSc in physics from Fergusson College in Pune, and then eventually I did my master's in physics also, and where I was doing projects and master's thesis on astronomy, and that eventually led to my PhD in observational astronomy.
So you really began, just before you started getting into your undergraduate course, you then collected a lot of information just even before that then?
Yeah, I talked with several people, several professors, as well as people in and around astronomy to gauge information about what are the possibilities, what are job opportunities and stuff like that.
Okay, so when you talk about this kind of capacity building in terms of knowledge sharing as to what are the opportunities and what are the streams, where do you see things can improve in India?
I think the public outreach of astronomy and pure science jobs in general needs to improve, and that there is very little engagement towards high school students or undergraduates about what are the opportunities available, even if you have not taken pure science route, that there are opportunities available for you to do astronomy or similar research areas, and that the engagement from the research institutes towards these high school students and undergraduate students outside of the big metro cities is essential, that it's not only focused towards big cities and big metros like Mumbai, Bangalore, Pune, things like that, while you are also targeting students in rural areas as well as tier 2, tier 3 cities.
Tell us a bit about, how is this being done in Europe or other countries where you have talent from, not even just the big cities, but also other areas coming in? Because I know that, many of the developed world countries have chosen to take a path of having dedicated science outreach people who are actually scientists who have done their PhDs and have been in the field and have contributed to the field, but then they have kind of switched their careers to do more of the outreach effort for science and becoming full-time science communicators, and then helping to develop the community itself, and the outreach for the community is being done by them. So this is a model that's been used in the Western world today a lot. What is a model that is possible in India? How could this evolve?
I think part of the limitation in India is that when you compare to Western countries, India has very few astronomy research institutes, and they are mainly located in big cities, and there are only a handful of them. While if you look at countries in Europe, for example, each small city itself has an astronomy institute, and most universities will offer you astronomy courses at undergraduate or master's level, while in India only a handful of universities will ever offer you any astronomy courses at undergraduate or master's level. So even if you are interested as a student to get into astronomy in India, there are very little opportunity available for you, because you either have to be in Pune, Mumbai, Bangalore, Delhi, or attending universities there, and only then you are able to get into astronomy. While in Europe, even if you are in a tier 2 or tier 3 city, it's most likely that the university there will offer you an astronomy course, and there will be actual working astronomers who are doing research, so you can go and work and do projects with them, whether it's a 2-month summer project or it's a long-term master's or bachelor's level project, and so on. So I think that is one of the things that is lacking in India. And in terms of science outreach, there are institutes who are doing a lot of outreach. So my experience is mostly with institutes in Pune, where Ayuka and NCRA are doing extensive and excellent outreach towards students in Pune, but around Pune, in rural areas, and also in Maharashtra and India in general. But again, one institute cannot simply do for the entirety of 1.3 billion people. You need to have a massive increase in the number of people who are working in this field, as well as surrounding areas of science outreach and similar topics where people are able to reach vast populations in India.
When you take the community of these three communities again, right? So the observers, the instrument makers, and the theoretical people, give us a sense about how big are these three communities in India against, the US, China, or other geographies. And where do you see more momentum in India in which of these streams, and what is lacking in each of these streams in that sense?
So in terms of the people working in these fields, you will have in each research institute in India and also abroad about 10 to 15 professors working on these areas, maybe sometimes more, sometimes less, depending on the size of the institute. And then with each professor, you will have few permanent staff working with them, and postdocs and PhD students and master students working with them. So in all, an institute will cover about 50 to 100 working staff who is directly working as a research work or instrumentation building and similar assisted work for that. So that's on average per institute. And then when you look at in total in India, there are very few institutes. So I would think about 10 to 12 institutes which work directly in astronomy or space research. And so in India, there are much less number of scientists working in this field compared to when you look at overall number of people working in North America or in Europe, for example, or even in smaller countries like Australia.
And is there a sense of the numbers there? So do you have any sense of numbers with these countries? Because, when you tell this, it sounds like the Indian space science, the core research community is about 1,200, 1,500 people in the entire country when you put that number together. So when you look at that number against, let's say, a China or a US, how does that stand?
Yeah, so in the US, you will find that in most states, there are at least few universities who are doing work in astronomy, and each institute will have few professors and several students working with them. So the numbers per institute are similar, but the number of institutes working in these fields is much higher. So in the US, you'll have approximately few thousands of people working in astronomy or related areas. And of course, in other countries, there is much more overlap as well as distribution of people, where people who are working in astronomy might also be not sitting in astronomy institute, but they might be sitting in a physics institute or a mathematics department of the university. So they may not be officially counted as astronomers, but their work is being done in astronomy.
Okay, so do you also have a sense of, the budgets that are allocated to astrophysics in India versus other countries?
Well, I don't have the exact numbers for each of these, but in general, India spends a lot less on scientific research as ratio of GDP compared to most of the Western countries. And in Western countries, the numbers are around 2 to 3% of the GDP is spent on scientific research, while in India, it's much less than that.
So if I am a high school student and I enter these three tracks today, let's say I want to do an undergrad which is related to astrophysics, what are the possible avenues?
So you can do either a pure science undergraduate, so doing a bachelor's, so BSc in physics or mathematics or related topic, and then do a master's and then PhD. So that's one way to go. The other option is that you can do an engineering in related fields, so either electronics or mechanical or something similar, and then go into instrumentation and building instruments for telescopes and similar. Or you can do computer science and work with theoretical physicists and theoretical astronomers and help them developing different new techniques, building software for astronomy, or working with machine learning and similar topics that are being used extensively in astronomy. So even if you have no experience in astronomy, you can still shift to that after doing a bachelor's in engineering in computer science or similar topics.
Okay, so let's say then you finish your bachelor's and so on, and you want to continue. You want to do a master program. I know that in India, for example, a lot of people drop off at that level, where they tend to do other things, or they have maybe social commitments to look after their family or so. So when you look at entering the master's track, the ratio, it goes down?
Yes, of course. Not everybody who gets a bachelor's degree in a physics or astronomy related topic will go for master's. There are different reasons for that, but in general, the number of people who will go for master's will drop by about 50%.
And can they continue in the same institutes, or then that also tapers off?
It depends. So many people in India at least do their bachelor's in colleges which are affiliated with the university, while most of them may not offer master's level courses. So they will have to go towards universities where you have dedicated departments which are teaching master's level courses. So you will have to go either to the state universities and study there for your master's, or go to central institutes like IITs or similar.
So again, with the master's done, of course, as an astrophysicist, you are only then going to graduate, in a sense that you, to contribute to research, you then take up a doctoral program and you are doing full-blown research. With that, do you have a sense of how many PhDs are being offered in India every year?
I don't have exact numbers again, but in general, each institute takes in about 10 students per year, and similar students graduate every year.
Yeah, so it seems like, we produce about anywhere, give or take, 150 to 100 astrophysics PhDs every year in that sense.
I would say less, okay. Maybe of the order of 50 to 100.
In the entire country?
Yeah.
Wow, that is like, considering that probably will be something like what a single state in the US would probably be producing.
Exactly. Or even when you look at institutes in Germany, for example, a Max Planck Institute has 65 PhD students at a time, and every year about 15 to 20 will graduate. And there are 3 or 4 Max Planck Institutes working purely in astrophysics in Germany, and then there are about 20 to 30 different universities which are also working in astronomy, each giving out similar number of students a PhD.
So let's say, I have managed to get into one of these universities in India and graduated. What are the possible options to continue?
So currently, astronomy is not the most lucrative field for doing your full-time research, in a sense that right now astronomy is going through a job crisis. So 90% of the people who will get a PhD in astronomy in the world will never get a permanent position in astronomy. So only 10% of the people who have their PhDs will get a permanent position as a professor or similar level at academic institutes. So 90% of the people will go and do something else. So that something else might be you can work as a science communicator, or work as different space agencies similar to ISRO or DLR in Germany, or ESA or NASA or something like that. Or you can move away from that and work in IT sector or data science or something similar. Some people I know have gone into science advocacy and working with the government, being science advisors. So there are multiple career options. The opportunities for you are very many, and the unemployment rate is very low. But if you have the dream that, okay, you want to be a professor in astronomy who is doing next 20 to 30 years of their career in astronomy, then the chances are very low. But getting a PhD is not simply about doing astronomy, but a PhD is teaching you certain techniques, tools, and getting to know about how things work. And then you can apply those tools in different careers and different jobs. And so you don't need to be restricted to the academic track. Essentially, you can use the same equations and do the same analysis working for a company rather than working on solving some astronomical problems. And I know several people who have done that, where they were applying the similar equations instead of using them for astronomy or physics, but applying to the finance market.
Yeah, exactly. I think this is also a very famous movie or documentary that I've seen where a bunch of private equity firms started hiring astrophysicists to crunch their numbers and use the data analytics techniques that they have used in their research to apply them to financial markets.
Oh, exactly. And essentially, many Western consultancy firms will hire you on a priority basis if you have a PhD in physics, astronomy, or mathematics.
Wow. Okay. So in India, ISRO is building all of these satellites that are going up, like AstroSat or other space telescopes that are being planned. How is the space community in astrophysics involved in with ISRO in building some of these instruments or using the data?
Yeah, so many institutes in India will help in building the specific instruments or specific detectors for these satellites, as well as building the entire structure along with ISRO. And they will help in that. And then once the satellite is up and running, then the data coming from the satellite will be used by Indian astronomers and scientists for analyzing the data and doing the scientific research.
Is this the same mechanism of working around the world, or is there different styles in working in different countries?
It's more or less the same mechanism in most of the countries, where the scientists will work directly with the space agencies for developing telescopes. For example, scientists in US will often work with NASA for building their space instruments and space telescopes, and then they will get to use the telescopes themselves.
Let's talk about the data that is coming out of these satellites. How is this data being shared? Because you said that the data is actually being used by Indian astronomers. In many of the cases, let's say in Hubble or many of the European space telescopes, they have a mechanism of also sharing it for people around the world. Is the instrument time being shared in certain way, or the data is being shared in certain way? Because of course you can also point the instrument to a certain part of the sky and image whatever you want, or collect data from there. And there's that time where you can actually use the instrument up, and then of course you can also use the data which is then dumped by some observer who used the telescope. So there are two parts to it, right?
Yes.
So how is it being done?
So essentially, all over the world, whoever has put the money to building the telescope gets to use it for most of the part. So for example, the telescope that I work for, which is the ALMA telescope, which is in Chile, it's built by North America, European Union, and East Asia together with Chile. So they get 95% or 99% of the time to use the telescope, and only in rare cases anybody outside of these regions will be able to use that. And it's similar to many of the Indian instruments also, that the priority will be given to Indian scientists to use the telescope, and in some cases people outside can use that. Of course, that is not the only way that you can do. One way is that you can collaborate with scientists from that country, and then you can use the data that is obtained by those scientists and do your scientific research. But in astronomy also, most of the data that is generated by these telescopes and instruments is proprietary for only short period, as in the scientists are allowed to use that data themselves for about 1 to 2 years, and then all the data becomes public. So once the data becomes public, then anybody all over the world can use that in whichever way they want.
So that proprietary nature of 1 or 2 years of having collected data, that is a national science policy, or is that an international phenomena?
No, it's a specific instrument policy. So each instrument or each telescope organization decides for themselves how much proprietary time they want to give to their users. So essentially, scientific observations are done in a way that if you are a scientist working, you have an idea, you write a proposal for that. So there is no money involved in most of the government telescopes. There are, of course, private telescopes where you have to pay a certain amount of money to use the telescope, but most instruments these days are built by governments. And so instead of somebody having to pay a certain amount of money, what you do is number of scientists will apply for their ideas, and they will submit a proposal to the telescope, and then their proposals will be judged on their scientific merit. And if your proposal gets accepted, then it will be observed. And then because you came up with the idea, you get priority for that, and that's your proprietary period. That, okay, you have the idea, and so we give you the data, and you can work on it for 1 or 2 years, and you get a head start. But after that proprietary period, anybody else can use that data.
Okay, and this is the same for also space telescopes?
Yes.
Let's say, today AstroSat is up and running. Are there any specific policies just at national level, which, let's say, the country decides?
I'm not aware of any of those. Essentially, in most cases, either the organization or the telescope itself will decide how the data is used. Of course, many of these telescopes are built by the government organization, so they are essentially national level or government rules.
So let's talk about actually what gets to be done with this data, or what science is done with this data. The value of the data itself is also attached to then the quality of the science instruments that are up on a space telescope or even the ground telescope. So give us a sense of, what is the quality, if that's the right word, of the space telescopes which are on the ground in India versus some other telescopes around the world, also the space telescopes.
So India currently has optical telescopes which are of the size 2 to 4 meters, which are considered to be medium-sized telescopes in the world. The current largest telescopes are built by North America, so mostly USA, and in the European case, it's built by the European Southern Observatory. So the largest telescopes currently available are the Keck telescope in Hawaii and the very large telescope built by European Southern Observatory in Chile. So these are the 10-meter class telescopes. So the diameter of the optical telescope is 10 meters. So these are the largest ground-based telescopes, but both of these countries are building the next generation telescopes, which are the 30-meter class telescopes. So there is a planned 30-meter telescope in Hawaii, which is being built by USA mainly, but India is a partner in that. So India has invested money in that telescope. So India will have a priority for observations there. While European Southern Observatory is building extremely large telescope, which will be a 39-meter telescope in Chile. And then there are, of course, the satellite telescopes. So everybody knows Hubble, which is, compared to the Earth-based telescope, it's a smaller class telescope. It has diameter of only a few meters. So I think 2.5 meters. While the next generation telescope, which will hopefully fly in a couple of years, is the James Webb Space Telescope, which is built by NASA. And that is a 5-meter telescope, which will fly to the Lagrange point L2.
And once the data is kind of collected in all of this, what is the quality of the output? How is it measured? How is the output being measured across different astronomy groups around the world?
So the quality of the data is essentially measured across how many papers it generates. So essentially the research output of the telescope is calculated by how many papers it has generated, how many of them have been excellent discoveries or sort of new physics has been found or something like that. So that sort of new discoveries and how many papers have been generated is one of the main criteria from which the telescope output is measured. But also in terms of how groundbreaking the results have been, as well as how useful the telescope has been for overall understanding of astrophysics for the community.
Can you give us a sense of what are some of the contributions that Indian scientists have made in the recent past in all of this?
One of the prominent contribution has been with the gravitational wave discovery, where India has been a partner in the LIGO collaboration, and Indians have contributed significantly in the data analysis and data reduction of the observations that are being done by LIGO. And so that is one of the main topics. India has also been involved in several next generation large scale telescopes. So India is partner in the 30-meter telescope that I mentioned, but also in the square kilometer array, which is a radio telescope which is being built in Australia and South Africa, which will come up in about 2025. And these sort of large scale telescopes are being built internationally because these are so big telescopes that not a single country can handle the expenses that these telescopes cost several $1 billion now. So the expenses for these telescopes are shared between different countries, and different countries will contribute various things. So for example, Indian institutes along with companies like Persistent are providing software support for the SKA telescope.
Why are some of these not, let's say, built in India itself? Are there some reasons for them?
Well, for building astronomical telescope, you need good atmospheric conditions. So for example, a lot of telescopes built by European Southern Observatory are built in Chile, because in Chile you have the Patagonian mountain ranges, which is 5,000 meters in height, where you can get above most of the atmosphere and you don't have to worry about atmospheric scintillation or water vapor or similar things too much. And also it's one of the driest places on Earth. Similarly, the square kilometer array is built in sort of arid desert areas with no human settlements around nearby, so that you're avoiding most of the radio interference from that. While India, there are places where you can build a lot of facilities, but they are not competitive always with international facilities. For example, in the Himalayas, it's quite difficult to build instrumentation, although we have a couple of facilities there. It's not always easy to build instrumentation in the Himalayas because of the remote nature, as well as not having good supply of electricity and other facilities which are necessary for running these kinds of observatories. And because of the population density of India, having radio-free zones are quite difficult to find in India.
Yeah, that makes sense. I know that there is possibly a facility in Leh which is operated through a satellite link, right?
Yes, but also in Ladakh we have a couple of telescopes in Hanle which are operated by the Aryabhatta Research Institute. So these are 2 and 4 meter class telescopes.
Space science missions, especially using satellites, have become extremely popular in India over the last 10 years or so, when ISRO started in a very big way by launching the first mission to the moon and then the first mission to Mars. And so now the second missions are being planned with Chandrayaan 2, almost ready to land on the moon's surface. And also next, the missions being planned for Venus and places like that. What has been the general quality of output of these missions? How could they be, treated so far in terms of value to the science?
Well, so far the space missions that ISRO has put forward have been mostly technology demonstration missions rather than scientific missions. So Chandrayaan and Mangalyaan both were technology demonstration missions with no guarantee of science coming out of them. So there have been few discoveries out of those. So for example, some of the instruments on board Chandrayaan discovered water on moon, as well as there was a discovery of methane in Mars atmosphere from the Mangalyaan. But both of these missions were technology demonstration mission with no goal for science. So there has not been much science coming out of them. But hopefully the next mission that is hopefully landing soon on the moon from Chandrayaan 2, that has main focus on science. So we are hoping that will lead to good scientific results.
So in that sense, India has kind of gone through this maturity of, establishing the technology needed to do interplanetary science, and then use the first missions to demonstrate that piece of technology. And now they're trying to do the more mature science-related aspects.
Exactly.
Let's talk about, Mangalyaan, for example, where it was such a big hype in the public, because there were so many analogies of Mangalyaan being cheaper than gravity, or cheaper than an auto rickshaw ride, and all these popular things that were going on in the social media as well as in general public. And of course, when you look at the science output of Mangalyaan itself, what is the science output so far specific to, let's say, Mangalyaan?
There have been few papers coming out of it, but when you compare with American instruments that have flown to the Mars, the science output has been negligible. As I said, the Mangalyaan was essentially a technology demonstration mission that proved that, okay, India can send a spacecraft to Mars and we are ready to do interplanetary missions. But that has been the main goal and the only goal, essentially. And whatever science comes out of it would be a bonus. So it has been a very small part of that.
So the roadblock there is that once we've demonstrated this technology, the size of the satellite also depends on the kind of instruments that you can host, right? Because basically, if you can host larger instruments, you need a larger satellite, you need a larger rocket, you need a larger budget, everything becomes large.
Exactly.
And therefore, is that the main bottleneck?
Yes. Primarily, that is one of the main issues, that when you compare with the American spacecraft that flew at the same time as the Mangalyaan, MAVEN, that had payload of 65 kilograms compared to 15 kilograms of Mangalyaan. So with extra 50 kilograms of payload, you can have very sensitive instruments which can last longer, as well as you have opportunity to send the spacecraft directly with the American rockets, compared to ISRO, which had to do multiple gravitational kick maneuvers and get into the position to fly to Mars. So by having larger capacity for sending instruments to Mars. So for example, India does not have capacity yet to send a rover to Mars, what Americans have done already several times. So if you want to do something like that, you will need a bigger and bigger rocket to be able to do that. And that is one of the main blockages for India.
When you look at the future of even space transportation, so all of it in space is so, at the moment, is then very interrelated. So because India then has to invest more into building bigger rockets, building better quality, to build better quality of satellites. And when it comes to instruments themselves, because I know that, okay, ISRO has proven that they are capable of building bigger rockets over time, having seen the maturity in rockets. And let's say they are going to produce this massive rocket that is needed for bigger instruments. And they're also able to produce the satellite bus that can be hosted in this rocket. Is there enough capacity in the country to build state-of-the-art instruments that will do state-of-the-art research, or are there bottlenecks there because we don't have certain pieces of electronics or certain technologies in the country?
I'm not sure there is a bottleneck. There might be shortages in the short term, but in the long term, India will have to develop all these capabilities itself and have to develop the industries surrounding the rocket launching industry as well as satellite manufacturing industry, and developing both intellectual temperament to develop the instrumentation as well as building capacity for developing both instrumentation as well as the scientific output out of that. So India will have to need to build that eventually on a sort of gradual pace. But that need not be the only way India can move forward. That many countries are enthusiastic about collaborating with India on putting their instruments on Indian payloads and working in collaboration with ISRO and similar. So just last year I was at a workshop on 10 years of Czech Republic in European Space Agency, and there was discussion on the India's Venus mission, and people were asking what are the possibilities of European community collaborating with India on this Venus mission. So there is enthusiasm from various communities all over the world for collaborating with India. So that may be a way for India to get forward quickly without having to worry about simply trying to develop everything indigenously.
Astrophysics may have been a dream of young people when they were growing up, but many of them may not have picked it up for their careers and they would have transitioned to doing other things. But then the love for space science would have been remaining with them. Is there a way for them to then get back as a hobby to do some astrophysics stuff?
Yes, there are several different avenues that people can take. So right now, one of the things that we are suffering from in astronomy is we have huge amount of data with not enough people to analyze it. In a sense that a lot of the analysis work is manual labor. Essentially, you have to look at different pictures coming out of the telescopes and categorize them, which is scientifically important, but that may not be the best use of a professor's or a researcher's time. So there are several different groups which have come up with ideas about crowdsourcing this, where citizen scientists who are interested in doing some science for themselves can go and volunteer their time and look into different pictures and analyze them, or look into different satellite image data and categorize them into different categories. So there is one interesting project called Zooniverse, where there are hundreds of thousands of pictures of different galaxies that have been put forward, and you can go and analyze different galaxies into different categories and then study them as you want. And then that is very helpful for scientists to understand the categorization of these galaxies. Similar thing has been also done with planet hunting and planetary science, where people who are working in exoplanet hunting or exoplanet discoveries are asking people to go through the light curves of coming from these telescope data from, for example, from Kepler or the next generation TESS telescope, where citizen scientists can go and look at the data and try to analyze it to see whether they have discovered a planet or not. And so one of the famous stars that is called the Tabby Star, which became very famous because it showed very weird dips in its light, and that led to several different sensational headlines in newspapers asking whether it's because of some weird planetary formation around it, or comets or asteroids around that planet, or whether it's aliens. Of course, it's never aliens, but it became very sensational, and that was discovered also along with the help of citizen scientists. So even if you are not a career astronomer, you can get involved in many of these projects where you can help scientists in improving the data analysis process. And then, of course, there are many other ways you can also get involved in your local communities. In many cities, there are many astronomy amateur groups where people are doing regular observations of the sky, looking at stars and planets and galaxies in their backyard or with smaller telescopes. So you can get involved in that. I know there are several groups which go for monthly or regular meteor shower observations to the countryside, and just organize also seminars or talks for general public, so you can get involved in those things also.
Yeah, and also I think as is with a lot of new fields like machine learning or AI and things like that, you see that possibly even astronomy is one big area of application there because you're sitting on top of tons of data, right?
Oh yeah, definitely. That has been something that we have been trying to do recently, is developing machine learning techniques to analyze certain data sets, but it's quite difficult and it will take some time to mature. So if you are interested in that, you can also get involved. If you have expertise in machine learning and data analysis that way, you can get involved in astronomical projects. But even many observatories and institutes will require engineering help in developing new softwares. So a lot of software analysis software that we have is developed in Python or C++. So if you have experience in software development, you can get involved in astronomical software development. So there are many avenues for you to get involved in astronomy in an outside way. And as I mentioned earlier, that, for example, the Persistent company is involved in developing the backend software for the SKA telescope. So even if you are working at a company like this, you may be working directly helping building an instrument.
Okay, yeah. And when you look at the future of possibly astrophysics and instrumentation in India, I know that, for example, the early bits of astrophysics and studies in astronomy in the US were actually mainly funded by philanthropic means, where many of the observatories in the US, which were in the 1800s or so, they were actually built by donations by several artists or celebrities or industrialists. Do you think in India, if in case the government is not really up for increasing the massive amount of funding needed in all of this, that's something is a potential avenue where people who are in the science community can actually convince some of the artists or industrialists to actually investing in doing good space science? In the US, not only in the 18th and 19th century, but even current modern facilities are often funded by different agencies which are outside the government. For example, the Simmons Foundation or the Sloan Foundation also funds a lot of astronomical research, and the Sloan Foundation funds the Sloan Digital Sky Survey, which is one of the most important surveys of galaxies that has been undertaken for the last 15-20 years, and that has been funded mainly through the Sloan Foundation. So there are several foundations in Europe and US which are providing support for astronomy and scientific research. And in India, that may be one way that people can get involved. And of course, we have the famous Tata Institutes and IISc, which was started by the Tatas and similar. So if there are billionaires who are interested in establishing institutes which have a long-lasting legacy, that will be a way forward also to get around the lack of funding from the government. Yeah, I really hope so, because I think to depend only on the government is a very long-term solution, I would say, unless and until there is radical change in investments into science. This may be one of the methods that I think the community in India should try to evolve and develop over time. Abhijeet, thank you very much for coming on the show.
Thank you so much for having me. It was a pleasure.